Can everybody hear me in the back? Is this volume good? Good for you? Okay. This is a talk about functional programming. I'm not using a functional language, a traditional functional language for this. The examples are in Java. I had to dredge out my Java syntax book and like Google for instance of, but we're set, we're good, and I think it's going to be a lot of fun. If you have any questions at any time, please interrupt me. It's going to be a lot more interesting if we actually have some discussion going on here. So jump up, raise your hand, shout at the top of your lungs. I'll repeat your question because I think we've got a few people spread out here, and it's, I don't know, it's going to be good. So selfish purity. We have all been in this situation. Every single one of us who's written any real software at all has been in this situation. We have a big ugly service in the middle of our code that connects to like 4 other services, brings them together. You know, maybe those services are injected or something. It doesn't matter. That's not the core problem here. The core problem here is we have this big ugly service. And there's some business logic in this service that defines like how we bring things in from the abstract Twitter factory bean and then connect things over to the like OAuth bean and like, I don't know, whatever we're doing. And this logic is something that we need to test. We care about testing this logic. We care about making sure that this logic is correct because our entire application will cease to function if it doesn't work. So we open up our trusty testing framework of choice, and we start working on testing this service. And we write mocks, and we write setup code. And 250 lines later, we are able to put 3 assertions in. And then we write 75 lines of teardown code, and we're exhausted because it took us a week and a half to write this one test, and we stop. And we have this giant, huge service that our entire application comes down to, and we have exactly 2 assertions for it, total. At all. 1 test case, 2 assertions. And this happens, right? This happens not because we're bad programmers, not because we're lazy and we don't want to write tests, but because it's incredibly difficult to test some of these things. Because they're gnarly and they're wrapped up inside things and the effects are tangled up with the logic and it's difficult to reason about it. We can't understand our own code. And it's very, 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 very difficult. And every one of us has been there at some point. What I am here to tell you is that I am far too lazy to do that. I've written code like that before, and it just exhausts the crud out of me. I don't know how you can do it. I have a tremendous amount of respect for people who are able to deal with code like that. What I do instead is what I'm going to show you how to do in this talk, which is I apply the principles of functional programming. So functional programming, as I hope we're going to come to see together, is not something about like, well, there's these mathematicians sort of at the dawn of time that laid down the principles of programming and we have to follow their word because they are the Messiah. No, functional programming is not about that. It's not about aesthetics either. Functional programming is about making our lives easier. It's about making it easier to do the tasks we have to perform on a daily basis. Write good code, write testable code, write maintainable code. We all have to do these things. We all have to write very messy maintainable code. And functional programming helps us do it better. It helps us do it more easily, and it helps us do it with less effort. And I am all about programming with less effort. That's what I'm here for. So we're going to talk about what functional programming is. Not going to do a mathematical definition. There's going to be no lambdas in this talk. We're just going to be talking about what functional programming is at its deepest essence. We're going to talk about reasoning about code. We're going to talk about testability, concurrency. These are the really, really big things that functional programming can make an immediate impact on how you write code. And then applying those principles can make your life substantially easier. So Albert Einstein defines insanity as doing the same thing over and over again and expecting a different result. I think that's actually kind of a really interesting definition, especially when you think about the fact that in the standard code that we write, in standard sort of software discipline, this is actually what we are doing. You know, it's called imperative programming or procedural programming or maybe object-oriented programming sometimes, but it's, you know, Albert Einstein probably would have called it insanity-oriented programming because we do things like this. We have a function, launch the missiles, and North Korea is gone. And then we call it again, and we get an out of missiles error. This is like something is profoundly strange here, right? We did the same thing 2 times in a row, right next to each other, and we got a completely different result the second time. And this happened because of side effects, right? And we can see just how profoundly weird this is if we just rearrange the code a little bit, right? We're going to introduce a variable. And when we introduce a variable, suddenly this code doesn't try to launch the missiles 2 times. It only launches them once, and then it just like gives us the launch status twice or something like that. We don't get an error anymore. The fact that these 2 slides actually have a different semantic, if you really think about it, is somewhat strange. That's really, really weird, and it means that whenever you see a line of code in your program, a line that calls a method, you have to have this extra warning kind of in the back of your mind. It's like, what is this method doing? Can I actually call it multiple times? And does this method maybe interact with this other method in some very strange way that I can't see, right? You have to remember all that stuff. That's hard to remember. What we would prefer to do is to have some sort of launch doer interface, right? Some sort of thing that represents launching the missiles, right? And so then the launch missiles function doesn't go off and send the missiles and flying or anything like that. It just returns a launch doer. And then we can have as many of these launch doers as we want. We can call the launch missiles function again. It doesn't matter. It's just going to give us the same launch doer because it hasn't launched the missiles yet. And when we want to launch the missiles, we have a function to push the button. We call that method, and then away things go. But we can now, once we call the unsafe launch method, then things are in trouble, right? Then people start dying. But before we call unsafe launch, this code is very reasonable, right? We can assign things to variables, and that doesn't somehow mess things up, right? So this principle, right? This ability to assign something to a variable has a name, and it's called referential transparency. This is the fancy functional programming name for actually a very straightforward concept: assigning something to a variable and being able to have the same result. It gives us something called equational reasoning. It means that if you take a method, right, and it returns x, okay, and then you use x at a bunch of places in your code, then you can just take that method call and substitute it in for x. Anywhere you were using x, you could just call the method instead. Or the opposite, right? You're calling the method twice, like we did with launch missiles. Now you substitute x. Equational reasoning says that works, and it gives you the same program. Formally, it looks like this. Look very carefully. This is the only math you'll see in this entire presentation. Be excited. Math. Rearrange your code without fear. Referential transparency is another word for safe refactoring, right? Our IDEs spend so much time trying to do this escape analysis and code flow analysis, and they run very, very complicated proofs, and they have really deep math that goes into it, fundamentally because most of our programs are not referentially transparent, and the IDEs have to deal with that work. Referential transparency means that you can safely refactor. It's easier on your IDE, and if you're not using an IDE or you're using a language that doesn't have one, you can refactor your code without fear anyway, because referential transparency, it just works. There's less magic. You don't have to worry about 2 methods sort of interacting in this strange way that I mentioned. So a very, very, very wonderful concept. Makes things so much easier. And a lot of FP, a lot of the benefits of FP come back to this very, very, very simple idea. I want to assign something to a variable. That's all I want to do. And that is actually a very profound truth about software development. So reasoning about our code. What do I mean by reasoning or reasonability? All that I mean is I want to be able to look at a block of code and understand it. I want to be able to know not just the instructions that it does, or the memory footprint or something like that. I mean, those are sort of implementation details. What I want to understand is, what does this code mean? What is it doing? What do can I understand it at a very deep level so that I can go and actually tweak it? I can change it. I can add a feature for a customer, or I can fix a bug. I need to be able to understand code in order to do those things. Reasonability is all about that. This code, I don't think is very reasonable. This is perhaps familiar code. I wasn't using any particular API, so the use of the term springy is entirely coincidental. But this is I think a relatively common pattern, or at least it was when I was doing this sort of thing, which is you have some DAO object. I even forget what that acronym means, and you start a transaction, and then okay, the transaction is started. I guess I have a thread local variable somewhere that's keeping track of that. I check my inventory. I try to set the inventory with this non-atomic function thing. That might fail because people might be messing around with the database while I'm doing it. I try to commit it. It doesn't work. I roll it back. I set a timeout, all of this stuff. Like this is a common pattern, right? We do these things all the time. Software has to be able to do these things. It's just commits, right? Two-phase commits. But reading this code and understanding what's going on here is actually very, very difficult. I have to understand what start transaction is, right? And the name sort of hints at it, but what if we had named it something else, right? What if I had a coworker who, wasn't so good with naming or just messing with me or something and named the function something weird? It'd be like impossible to understand this. That would be super annoying, and it would be really, really difficult to know where to go with this code, how to maintain it, what to do with it. I don't really know. Check inventory. These things are weird. So, what we want to be able to do is we want to be able to take code like this, because we have to deal with code like this, because it's our job. This is what we do. And we want to kind of massage it into a shape that's a little bit easier to reason about, a little bit easier to understand, a little bit easier to know, okay, so the transaction starts up when we say start transaction, and the transaction stops when we try to commit. Just even understanding those basic things can make code much easier to understand, especially if you're seeing it at a glance. So we refactor things. We refactor the transaction API. And now we have something that's maybe a little bit more verbose, because Java likes having this anonymous interclass verbosity thing, but you see the idea, right? We say transact, and we give it a transaction object. And inside that transaction object, we have just the logic for our transaction, now separated from the logic of retrying and committing and whatever else it is that we have to do. And inside of that transaction block, we have the inventory check and the non-atomic set and things like that. So this is better, I think. I would argue that this is better because we can see the scope of the transaction lexically at a glance. The compiler will enforce certain things about this, even the Java compiler, and the DAO is able to have the transaction as a single entity. It doesn't have to do any thread local things anymore. It can just run it in a single scope. So we may, in fact, get better performance out of this even, because we don't have to fall back on some JVM magic in order to make it work. But we can still do better, right? There's a weird dependency here that is kind of uncomfortable when you look at it, which is the check inventory function, right? So the check inventory function appears to do, I don't know, I'm trying to understand this code as I'm looking at it, right? But my guess would be that the check inventory function checks whatever amount of cement that we have in storage, right? And then if we don't have enough to pour the load that was requested, then we'll throw an exception, I guess, and fail the transaction. I don't know what we're doing here. I'm guessing it's throwing an exception because it's not connected to anything. Connecting it to things will make that clearer. We'll make it easier to understand, right? We have to guess what this function is doing. We do this all the time, right? We look at code, we're like, oh, I guess it does this, that seems reasonable, and we go with that, and then bugs get introduced because we make mistakes. Making fewer mistakes can be enabled by tying things together, by eliminating some of that guesswork. And we can do that just by restructuring our code a little bit. So here we're going to make it a little bit more verbose, but it's a little bit safer. It's more reasonable. Now the check inventory function isn't throwing an exception anymore. It's just returning a Boolean. It's very, very, very straightforward change. Maybe we could have it return something more interesting, like an inventory status, had some sort of error message inside of it if it found not enough concrete exception. I don't know. But a Boolean is certainly the simplest thing it can do. And now it's really explicitly clear that we have to check the inventory before we can set it. And these two things are tied together. And the check inventory function isn't going to do anything strange. So again, right, this check inventory function now, presumably inside of there's just like sort of a less than, greater than, numeric equality test, right? If it's really that simple, then we could take the check inventory function or the result and assign it to a Boolean variable, right? The referential transparency thing that we were talking about. We can rearrange this code without fear, right? We can move things around and make it look better, and just the things that we want to be able to do. And of course, then there's the retry transaction thing, which this is probably getting back into magic territory, because I'm guessing like the only way to implement that is to throw an exception. I don't know, but at least we got rid of the springy annotation, so we can drop the springy framework from our dependencies, I guess. I don't know. I think we've moved forward, the functional purist in me, the person who's like, oh, beautiful Haskell, shades of gray, whatever. Like that person looks at this and is like, oh, well, we could do so many other things. But functional programming doesn't mandate that you shave your head and wear a robe for the rest of your life. You don't have to go completely off the deep end and change all of your code to be pure and monadic and threading things through with lambdas and higher order context. You don't have to do that. You can take small steps. You can take incremental steps, and you can just make your code better using the principles of functional programming. A lot of this stuff that I'm going to show you, especially if you've kind of been experienced in the industry for a long time, it's just going to look like, well, I'm just making the code better, right? I'm just doing very simple things, and that's what functional programming is all about: making things better, making things easier. I wanted to talk about, with respect to reasoning, I wanted to talk about reasoning in the small versus reasoning in the large. Because this is, it's a little bit of a sidetrack from the code that we had, but I think this is an important topic of discussion, right? So reasoning in the small is like, I'm looking at a method. And this method is doing some very simple things. It's not in some sort of big, scary service that's connected to a bunch of other big, scary services. It's like some simple thing that's talking to a database or something like that. That's reasoning in the small. You're reasoning at the level of like these little instructions, right? And with imperative programming, our instructions, our very basic building blocks, they're stateless. They're predictable. Your if statement does the same thing all the time. It's you see an if statement, you see that keyword highlight, and you know what it's going to do, no matter what context you see it in, right? So instructions are stateless and predictable, and they're very, very easy to talk about. They're very easy to reason about because they always do the same thing. Services, for lack of a better term, tend to be stateful. They're large, and when you see them, when you see a method that's calling these DAO functions or abstract Twitter service functions or something like that, that sounds very complicated, right? There might be something inside of that. Maybe you have to initialize the service before you can talk to it. Has the service been initialized yet? I don't know. I guess I better check. That kind of reasoning is very difficult, right? We saw this a little bit earlier with the start transaction and commit things. That's very difficult to reason about. You can't always rely on things doing the same thing every time you see them. And so with an imperative programming style, with an imperative structure to your code, reasoning in the small at the level of instructions, reasoning in the large at the level of services is actually something that's different. So it's actually very scary. People talk about, you're getting hired on by someone and they're saying, oh, we have a 3 million line Java code base. That actually sounds really scary because you probably have a lot of code in there, right? It's not because Java is scary, it's just because there's a lot of things that you have to keep in your head. In order to look at any one part of that code, it's very complicated, and reasoning about one part of the code means understanding a ton of it, like how the state lines up, right? And I don't know, I think that kind of means that it doesn't scale very well, right? That doesn't mean Java doesn't scale, it just means that programming in this sort of style has its warts and doesn't scale in terms of reasoning. If we go to the principles of functional programming, though, we kind of lose this dichotomy. So in functional programming, when you're working at the small level, you're working at the level of expressions, right? You have an if expression. You have, a function call expression, application, lambdas, those sorts of things. Those are expressions, right? Expressions, like instructions, are stateless. So just like instructions, they're very easy to work with. So imperative programming and functional programming, completely even terms, completely even footing in the small. However, when we get to the large, we have functional programming that gives us expressions, which are stateless and predictable. This is the beauty of really pure functional programming. This is sort of the holy grail that all functional programmers strive towards, is the fact that when you're working with big, scary, abstract Twitter service, you don't have to carry any more context or state in your head than you do when you're working at the level of utility function that manipulates something on the disk, right? It's just the same. It's not any harder. So working on a large functional code base feels exactly the same as working on a small functional code base. Wouldn't it be great to hear the words 10 million line Java code base and not shiver in fear? Like, that's what I'm proposing, and that's what these principles can help us do, and make it very, very easy to understand code bases. It's still hard, it's still programming, it's not a panacea, but it's easier. It's just easier to work with. Testing. I talked about testing at the beginning of the talk. Testing is really important. Really, 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 really important. And I think we as an industry, we do well at this. We could do a lot better. I think all of us could do a lot better. I'm certainly guilty of rushing code into production that's like, well, I just changed what the button did, and I don't have to write a test for that. And then it gets into production and then it doesn't work. Or it like works, but it only works if the color isn't blue or something like that. Like testing is really important, and we need to do better with this. So any steps that we can take in our own methodology that make it easier to test, that make it more pleasant to test, that make it safer to test, those are steps that we should take. So here's a typical example, or at least typical example for me. You guys probably write better code than I do. iMessage service, right? Not to be confused with message service. So iMessage service, we have this init function, and we appear to have some sort of enqueue function that takes a message and stuff, and then periodically, I guess, we're flushing it to a disk or to Kafka or something. I don't know. We're dumping it out someplace. Typical sort of service thing. Testing the flush method is actually very difficult, just given this interface, if you think about it, right? So how would you test this, right? You'd in your setup, you'd call init, you'd have an instance of the service in your unit test somewhere, and then you'd like enqueue a couple messages, and then you'd try flushing, and then what? Would you read the database to see if the message queue had flushed to the right place? And if you decide to use a different implementation of iMessage service, maybe one that doesn't write to the database, do you have to like change the test to read from a different source? And what if that source is sort of unreliable in your CI server? Like, it's madness. It's very difficult to do this sort of thing. It's hard, legitimately hard. So testing this stuff is very difficult. So how do we make it more testable, right? How can we make little steps to make it more testable? Well, ignoring for the, well, actually we don't even have to ignore for the time being. Let's just go ahead and do it. What we can do is we can make flush actually return something. So just like with launch the missiles, right? Remember, launch the missiles sort of wasn't returning anything useful. It was just throwing an error or something. And then we changed it to return a launch doer. Here we're changing flush to return a message sync, right? So we flush the message service, and then the message service presumably writes out to something, whatever that something is. I don't know. Well, let's look at what that something is. Message sync. So all message sync really has to do is it has to be able to receive messages from the message service, right? Or from whatever's writing into it. So you write a message into a message sync, you get a new version of the message sync. So or maybe you just return this. I don't know. I just want to give you some extra flexibility. You can implement this however you want. And the beauty of this is you have the ability to implement this in different ways. Right? I mean, this is going to sound a little bit like dependency injection. This is going to sound like, services and what the point of service interfaces and programming to the interfaces in the first place. And it is. That is the point of dependency injection. That is the point of programming to the interface. It's just that we forget sometimes, and we sort of stop programming at the interface at the service level, and then we're inside of the methods of the service, and we're like, oh, I'm just going to program this like it's C again, and then that doesn't quite work out so well. This is kind of pushing it down to a further level, right? Keeping your abstraction boundaries really clean. And believe it or not, it's something that functional programming explicitly pushes towards. towards. The practices of functional programming are all about this. So you build an in-memory message sink, right, that has the ability to read these messages, and now you can test it. Now it's very easy to test it, right? You just create the iMessage service, you make sure it's creating an in-memory message sink, and then you just read the messages out when you're done with the test. You don't even have to go to disk, right? Your CI server doesn't have to worry about latency. Everything is easy. Everything is really, really easy. So the lesson here is basically just this, that side effects are difficult, right? Side effects are hard to observe. And by side effect, I mean Korea being destroyed by my launch missiles function. By side effect, I mean the database being modified by the flush function, right? Those things are hard to observe. We have to go out, we have to connect to things, whatever. I mean, maybe we have to mock things and we have to use some sort of like bytecode injection thing to like dump stuff over here and then remove it later. That's hard. That's hard to get right. And it's fragile sometimes and it goes wrong. And it's just, it's very, very difficult and error prone. So rather than trying to test these things that have their logic tangled up with the side effects, right? The logic being what messages we flush and in what order. What we really want to do is we want to lift our side effects into data. Because data is something we understand. Data is something that's in memory. Data is something we can sort of introspect and get our hands on, right? We can look at this data. Data is easy. Side effects are hard. So let's work in terms of data. Functional programming is all about this. This is like what functional programming really encourages us to do. It's like, don't do effects, just do everything as data. Everything is data, more data everywhere, right? So lift your uncontrolled side effects into data. In this case, the message sink thing, right? We're writing messages directly into the message sink. The message sink records that, and then we can look at it later. And then you can evaluate this data in production, right? So you're writing it out to the database, you're performing the effects, right? Because your users want to be able to see that the data is written, you need to persist the data. But in tests, it's very easy to just not evaluate it. Look at the data, walk over it, interrogate it, see what actions were about to be performed, were going to be performed in production, and then you don't have to worry about actually trying to observe the outside world. Here's an even better example, I think. So here's a file system abstraction, right? Maybe you could implement this file system abstraction on top of the file system, or perhaps you could implement it on top of Hadoop or like some document store somewhere. I don't know. Like, yeah, I mean, you can imagine a bunch of different ways to implement this. So it's nice to have an abstraction for it. So we have this abstraction, but again, we have what's implied in these abstractions, what's implied in these method signatures is. It's sort of this side effecty thing that it's going to be hard for us to test, right? How are we going to test the create file function? How are we going to test the write function? Are we going to like create a temp directory and then point our file system service at the temp directory and then like try to make sure that it created the right file in the right place and then update the implementation? I don't know, like that sounds hard. It sounds very hard. Rather than doing that, let's just go back to the principle of taking our side effects and moving them into the level of data. So every single operation here, rather than just returning void, we're going to transform it. So we return something called FS logic. So file system logic just represents, a series of actions that we're going to perform against the file system. And it's just really, like, FS logic is just going to be really trivial, right? It's going to be stuff like, well, we have the ability to touch a file and make sure it's created. We have the ability to read data, write data, delete files, like just simple stuff. It's really trivial to do this sort of thing. And the key thing being that every FS logic has the ability to get the next FS logic in the chain, right? So it's kind of like a linked list where we just, you can represent this in many ways. Maybe you want to return an array of FS logic, however you want to do this. Just every single file system command has the ability to return a series of instructions, but it doesn't actually run those instructions, right? It's not going to disk. It's not going to Hadoop. It's just giving us these instructions, and we'll be responsible for dealing with them later. So a concrete file system implementation is actually very, very straightforward then, right? You just create the instances of FS logic. It's just really, really, really easy to implement. And there's no messing around with service connections or networking or disk access or anything complicated. It's very, very easy. And then we write this function, evaluate, right? That takes an FS logic, and this function is living somewhere, it doesn't matter, but it takes an FS logic and a file base path, and it's just going to run the FS logic against the disk, right? So when it asks us to read a file, this evaluator is just going to like open a file input stream or open a file channel or something like that and read the data off the disk and give it to us. Just really, really simple stuff. But the important thing is that this evaluation function is separate from the I file system, right? It's separate from the I file system, which means that if we want to test the implementation of our file system, if we want to test the logic that, when we move a file non-atomically, we read the old contents and then write them out to the new file. We want to test that bit of logic. We can do it without mocking out the file system or dealing with disk or anything like that. We can just do it by reading the FS logic. We get the FS logic back, and our test just looks at, make sure, oh, the first one is a read. Oh, the second one is a write. We're done. And it's very, very easy to do this. Makes your tests very, 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 very straightforward. This is a general pattern. It's called defining an algebra of operations, right? So this FS logic thing, that's what an algebra is. That's all it is. And so functional programmers, especially when they're talking about category theory, they kind of get this dreamy look in their eye and they're like, the algebra. Define the algebra. This is actually what they're talking about. It's not really all that dreamy. It's very straightforward and obvious. And this is how you do it. Your algebra should be very simple, right? If you think it looks stupid, you probably did it right. You want it to be as easy as possible to work with. You want your tests to be able to look at it and understand. Very, very straightforward to understand. And you write two interpreters for that algebra. Your first interpreter is run the thing on the disk, right? This is your real interpreter. It's do the effects, call out to Hadoop, block the world, whatever it is that you're doing, launching the missiles. And then your fake interpreter is just tell me what you're doing. Just tell me what instructions you performed, and I'm going to run some assertions about whether or not you're performing the correct correct instructions. This is very, very, very easy to do, and it allows you to do things in a very powerful fashion. Time for the M word. Monads. Free monads do this. And this is all you need to know. So when you're excited about this and you're looking up things before and someone on the internet in an IRC channel says, oh, free monads, it's this. This is what free monads are. They allow you to, they're a tool that allows you to do this in a syntactically nice way. That's all it is. The really interesting thing is not the monad bit. It's not even the free bit because, I don't know, they're cheap. The interesting bit is the algebra, defining the FS logic thing. That's the thing that you should hold on to because that's the important lesson. And that's very easy to do in any language. Java, C#, whatever. All of these languages have the ability to do this. So, concurrency. Concurrency is I saved this for last because concurrency is the poster child of functional programming, right? Everybody runs into this multi-core and multi-server and multi-data center thing, and they talk to people about what are we going to do? And then, oh, okay, it's not working anymore. We'll just go with functional programming and you do actors and reactive something and callbacks and Node.js and the functional programming is really hot because of concurrency. So as you would expect, there's some really, really good examples out there of how you can make concurrency easier with functional programming. But at the end of the day, concurrency is hard. Concurrency is very hard. And functional programming, it's going to make it better, but it's still going to be hard. All functional programming can do is make some things that are complicated less complicated. So here's the canonical example, right, of where you can do things with functional programming and concurrency. Very, very naive bit of multi-threading here, right? In fact, so naive that we don't even start the threads. So there's a typo, there's two typos in this example and it will never run. So that's the lesson for today. Functional programming makes your code run. So what's happening here, if this were actually working correctly, is we're computing two different things, right? We're computing some sort of left side value. We're just computing one thing with some input and then computing some other thing with some input. And we're taking those results and then we're putting them together and then we're computing something with both of them, right? We're using both of the results that come out of this. Really straightforward example. A lot of concurrency kind of boils down to this. This is the metaphor that the fork join name is meant to invoke, right? Is you're supposed to think about this case. You have two threads, one goes off here, one goes off here. They come back, you're waiting for them to come back, and when they finally get back to you, you do something with the result from both sides. But this is really, there's a lot of kind of clumsy ceremony here, right? We have to create this results array, apparently, to get the results. We probably are worried a little bit right now, like I am, about whether or not the cells of the array are volatile, because memory barriers are confusing. We have to spin up these threads, and then these threads are not on a thread pool, so what the heck are we doing? And are we going to thrash? Is this in a hot path? And then we're joining on these threads, so we're actually like blocking our thread, waiting for them to get back to us. It's just really complicated. It's very difficult. And if we wanted to do something even more crazy, like take this result and do this entire thing in parallel with something else on the side, and then wait for the results of both, right? Like another branch in our fork join thing, that would be even harder. So this doesn't really compose. What does compose are futures, right? Not the futures that were sort of introduced back in, I don't know, Java 5 or whenever that was. I'm talking about like actual functional futures, right? Monadic futures. And these are something that you can get from Akka. You can get them from various places. Like there's a lot of libraries that do this. This is Akka's library here. And what we're doing here is we create a future on the left-hand side. We compute the left-hand side. We create a second future that computes the right-hand side. And then down at the bottom in that morass of angle brackets, we have a zip function call, right? We take the F1 and the F2 and we zip them together. It's right down towards the bottom there. And zipping them together says, hey, I need results from both of you. I need the result from F1. I need the result from F2. It's inside of you somewhere when you finish computing it. I don't care how long you take to compute it. Just both of you go off and do things. And when you both come back to me, I will awaken my thread and we will continue the computation. And this is powerful. It's very verbose, though. Very verbose. And this is where you start seeing the limitations of certain languages, like Java, for example. Without using Java's lambdas, which I could have used here, right? Java 8 lambdas would collapse this down to like half a line. But without actually using some different language features, this is going to be clumsy. So I'm going to show you what this example looks like in Scala, just because I want you to see what it can look like in languages that have support for this. So we're just going to take a detour. There it is. Okay, Scala. It's much more concise, but it's concise because Scala was sort of built with these principles in mind, right? This is what a language can do when it's built with functional principles in mind. It has the ability to take callbacks, right? Take lambdas, which are these Clojure, things, the things inside the curly braces. And it has the ability to pass those as a parameter to functions. So it makes it easier to do stuff rather than using anonymous inner classes. Java 8 lambdas do exactly this for us. And Scala has this pattern matching thing, which is it's not necessary for functional programming, right? We've been doing functional programming throughout this entire talk without pattern matching. But it makes things easier, especially when you're dealing with algebra. Here's what's really cool. This is the version of Scala that corresponds to the Java example that we had, where we had the two futures going off to the right and then thing. But what if we wanted to take the result of this and then derive a new result from that and then return that as a future? Well, that would get really hairy, right? A lot more complicated. But we can do it in a very straightforward fashion using these four comprehensions, right? And these four comprehensions are using a function under the surface called flatmap. So zip and flatmap are kind of the two fundamental functions here. And this is really important. Zip and flatmap are very fundamentally interesting things when it comes to talking about control flow. And control flow is all about concurrency. So while we've been talking, right, I've been kind of giving these visual metaphors of like, you're going off to the left and you're going off to the right, and then you wait for the two things to come together. You bring them together, right? Those visual metaphors, that's exactly what the code is doing, right? They're metaphors of the actual control flow that we want. Like, okay, do the same thing at the same time. Okay, now, take that result and then go down to the next thing, right? You should have this very vivid diagram in your head. We want to take that diagram and make it real with code. Because if we can represent our control flow as data, as these function calls, then our library, in this case the futures library, can do cool things with concurrency, can do cool things that care about control flow, which concurrency is one of. So for computations, for control flow, right, there's two different paradigms of control flow that matter, right? There's the sequential one, where you have a value and you want to compute a new value from it, right? So just one line straight down, and you do that with flat map. You do that, that's the for comprehension thing. Haskell calls it do notations. Python calls it yield. I mean, there's a lot of different implementations of it out there. But this is sequential control flow. It's all about the sequential control flow, one thing after another. Parallel control flow is where you get concurrency, right? Because you can't really have much concurrency if you have to wait for this computation to finish before you move on and do the next computation, right? You have to have that fork. And this you get with zip. So the zip function is the one that says, okay, I'm going to take two futures and just run them as fast as I can, and then as soon as they're both finished, I'm not going to wait on either one, but as soon as they're both finished, I'm going to have the results. This is what the zip function does. And functional programming, the functional programming community has found these particular functions, right, this notion of sequential and parallel control flow, to be so useful and powerful that we've created this special name for it, these special abstractions. So we can talk about the general class of things. These are the things that have sequential control flow. These are the things that have parallel control flow, right? Sequential control flow is monads. So when someone says to you, monads are burritos, they're saying to you that monads have sequential control flow. I don't actually know what that has to do with burritos, honestly, but apparently that's a thing. Monads are just sequential control flow. It's like, I have this thing, I'm going to compute the next thing in a row, boom, just like that. Parallel control flow is something called applicatives, right? It's not as catchy of a name. It doesn't sound like certain vulgar English words, and so it doesn't have as many tutorials about it. But it's good and it's important. It's arguably more important even than monads because it allows you to do these really powerful concurrent things. These two abstractions are why concurrency is good in many functional programming frameworks and many functional programming languages. These two abstractions are how it works. And so when you start thinking about concurrency problems and you're like, I want to be able to do these things in parallel, but I don't know how to structure my code to do it, because that's a hard problem, right? Concurrency is hard. What you should think about is try to think about your problem in terms of control flow. Try to think about where is it sequential or monadic, where is it parallel or applicative? And then look for the tools that correspond to that. So in Aka's futures, that zip and flat map, there's various tools out there, and they all boil down to this. This is where the whole fork join concept comes from, is this stuff right here. So keeping these principles in mind is what enables you to write really good concurrent code. It's what enables you to design algorithms very naturally for concurrency. So that's really, 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 really nice. Again, making hard things still hard, but slightly less hard, hopefully. I don't know. Wrapping things up, okay? We've hit a few points here. What have we hit? Behavior that differs situationally is confusing. You look at a function, that function does something different under different contexts. That's weird. It's very hard to understand. You have to keep track of so much stuff in your head. So that's difficult. Data is good. Data is awesome. Data is very easy to manipulate. It's easy to understand. There's no surprises. It's right there in front of you. It's just memory. And you can look at it and interrogate it and assert things about it, and it's fast. And you don't have to put timeouts in your CI tests. And it's great. Use data. When in doubt, make it data. That's everything. Effects are not data, right? Writing to a disk, that's not data. So make it data, and you make it testable. You make it understandable. You make it easier to work with. This is the entire principle of practical functional programming. Make it all into data. Think about control flow. Concurrency, think about control flow. Is it sequential? Is it parallel, right? What do you need to worry about at different points, at different junctures? What are your data dependencies? That's all control flow. And the concurrency will come from that, right? Control flow first, concurrency happens then. Like I said, all of this stuff, all of these principles, they're all about making things easier, right? Making you have to work less hard, making it easier to avoid bugs, make it easier to maintain your code. That's what this is all about. That's all I really care about. That's the only reason I do functional programming, is because it makes my life easier. It makes the life of my coworkers easier. So with that, are there any questions whatsoever about anything at all? Haskell, concurrency, I don't know, stuff, Spring. I don't see any questions whatsoever. Oh, one question there in the back.
Yes, my question is, why do you bring up monads as the sequential control flow? Why not? Can I just use, I don't know, statements one after the other? Why? Yeah.
So the question is, why do I use monads as the example of sequential control flow rather than just statements one after the other, right? Statements can be easy to reason about, right? That is an excellent question. So here's the problem. In order to have these concurrency semantics, right? In order to have this notion of a computation that if we zip it together in parallel, it'll be parallel, right? In order to have that notion, we need to wrap stuff up inside a container. So in this case, that container that contains our computation is future. But the problem is then that our data is inside of future, and we want to put two futures together. So we can't just like put two futures on the same line, one after the other, right? Because the data is still inside of them, right? And we want this future down here to be computed from this future up here. So how do we do that? And the function that allows us to do that is flatmap. So that's the whole purpose of that. That's the whole purpose of that function. Excellent question. Very, very good question. Some people like to talk about statements as being like a form of monad and like the semicolon operator. I find that metaphor enormously confusing, which is why I'm mentioning it now. But there is a very tight connection between the two. Good question. Anyone else?
The real question is why if we want to use future, we have to use a different function that if we don't want to use future.
So the question is, we're using future, we have to use a different function to manipulate future, to put them together, for example. What if we don't want to use future? I don't understand.
So the question is, basically when you choose to use future to do something asynchronous, you can't reuse
Yes.
a higher order function.
Yes. 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 Good. So the question is basically, you choose to write something in terms of future, right? You choose to write a function that manipulates two futures, like puts them together, or, maybe manipulates a collection of futures and does something interesting with that. Now that function is written in terms of future, and you can't use that function on things that are not futures, right? Maybe you have some computations that aren't performed in the future. Maybe they're performed in the present or even the past. How do you manipulate them together? Yes! Oh, that's such a great question. Functional programmers have a way of dealing with that problem, and it's called higher order programming, and it uses the monad abstraction, right? The fact that we know that all of these things that have a flat map function, all of these things are monads, right? So it's like programming to the interface, right? Rather than writing something specifically in terms of future, if all we really care about is these two things that we're getting, all we care about is that they have flat map, we'll just write it in terms of the monad abstraction, right? And functional programming languages have really good tools for doing this. And once we write the function in terms of the monad abstraction or the applicative abstraction or whatever abstraction is appropriate for our problem, then we have a powerful function that we can apply to many different things, not just future. Oh, that's such a good question. Thank you.
Yeah, there is a problem with monads, which is the monad it's only a way to hide one thing. You can hide future or asynchronous things in a monad, but if you have something like checked exception, which is another kind of monad, how do you compose?
This is very, very, very good question. So the question in this case was, monads are good, or monads and applicatives in general, type classes, right, are really good for, or type constructors, really good for encapsulating one notion. Future encapsulates the notion of asynchrony, right, being able to run it in the future, deferred computation. Option, or maybe, right, optional in Java, encapsulates the notion of, maybe you don't actually have a value here. And there's monads for doing exception handling and things like that. But how do you do two of them at the same time, right? What if you have a computation that's, deferred, it's performed in the future, and maybe it returns nothing, rather maybe it returns something, and maybe it throws exceptions, right? So you have three monads that you want to put together. How do you do that? That is an excellent question. And the blanket stock answer to that is monad transformers. It's an incredibly scary thing that puts type lambdas on the page, and oh my gosh, they're confusing. There is not a good answer to that. Monad transformers don't qualify as a good answer. They qualify as an answer, and they work, but they're really, really hard to work with. So, open research problem that papers were literally submitted to conferences last year about. So, very, very good question. I think I may be out of time, so one more question? Anyone? Be congratulated by me? All right, thank you very, very much.